Everybody, and welcome to a place where light doesn't always lead the way, and the stars only tell part of the story. Tonight, you're floating through the dark, a real kind of dark. Not the cozy bedroom kind. I mean the cosmic kind. Out here, in the vast vacuum of space, something massive is pulling at everything, and yet, you can't see it. Not even a glimmer. It's like the universe is playing a trick on you with invisible hands. You're drifting near the edge of a galaxy now. Feel that slow spin beneath you. Galaxies rotate, you know, majestic spirals twirling in the void. But here's the twist, the way they spin shouldn't even be possible. Not without something extra. Something hidden. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, tell me where you're watching from and what time it is in your little corner of the cosmos. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You feel it right away, the cold emptiness of space isn't empty at all. It's full of secrets. Full of mass. But not the kind you can hold in your hands. There's no glowing surface, no shimmering outline. Just a pull. Gravity. It clings to you even when nothing's there. It's like being tugged by a ghost. The stars around you don't behave. They're too fast. Too confident. Like a roller coaster that never slows, even at the edges. Scientists looked at those spinning galaxies and scratched their heads, because all the visible stuff, you know, stars, gas, dust, simply isn't enough to keep everything together. Those stars should be flinging off into space like glitter from a blender. But they're not. They're anchored. Suspended in rhythm. Why? The answer, at least the one most physicists agree on, is dark matter. Mysterious. Unseen. Supposedly making up about 85% of all matter in the universe. That means everything you can see, planets, moons, cats, cake, you, makes up only a measly 15%. The rest? It's invisible. It wasn't always like this. Before the 1930s, nobody was really thinking about this stuff. But then a Swiss astronomer named Fritz Zwicky took a look at the Coma cluster, a giant bundle of galaxies just casually existing in space, and noticed something odd. The galaxies were zipping around way too fast to be held together by their visible mass alone. If normal matter were the only player, the whole cluster would have torn itself apart long ago. But it hadn't. It was stable. Zwicky's conclusion. Something else, something dark, was adding mass and holding everything together. Historians still argue whether Zwicky was taken seriously at first. He was, let's just say, not the most tactful guy. He called people spherical bastards because they were bastards from every angle. Charming. But the idea stuck. Dark matter. A term born from frustration and mystery. And the name itself? It's misleading. Dark implies black or shadowy, but this matter doesn't absorb light. It doesn't reflect it. It doesn't do anything with light. It's more like invisible matter. But dark had a nice spooky ring, and so it stuck. Scientists and sci-fi authors alike couldn't resist. Now, you might ask, wait, what if we're just wrong? Great question. What if we've miscalculated gravity? Or maybe the universe isn't playing fair? Those are real debates we'll get to later. But for now, just feel yourself moving, slowly, among stars that shine bright, held in place by something that doesn't. Even the way galaxies cluster hints at hidden mass. They clump together like sleepy penguins on a chilly planet, pulled by something more. You can't see the rope, but you know it's there. Let's get personal for a second. Reach out in your mind. Touch your own body. Everything that makes you you, bones, blood, breath, is made of baryonic matter. That's the science word for normal, everyday atoms. But your atoms are rare in the cosmic sense. They're special. Exotic, even. Which is ironic, right? You're the oddball in a universe full of invisible stuff. And just think, the next time you look at the night sky, you're not just looking at stars. You're looking through an ocean of hidden mass, like peering into fog made of silence. But don't worry. You probably won't survive long enough to figure it all out. You're still drifting now, gently orbiting the outer rim of a spiral galaxy, not unlike our own Milky Way. It's beautiful here. Swirls of starlight curling outward, delicate like spun sugar in space. But don't get too hypnotized by the glow. Focus on the speed instead. You watch as stars whip around the galaxy's center, far from its gravitational heart, and yet, they move just as fast as the ones near the middle. That's not how physics is supposed to work. Think of a merry-go-round. The horses near the edge should move slower to stay balanced, or get flung off into the playground. But these stars, they break the rules. And they've been doing it for billions of years. This isn't just one galaxy misbehaving. It's all of them. Every time astronomers point their telescopes at a spiral galaxy and measure the speeds of stars, near the center and out at the edge, they get the same spooky result. Too much speed. Not enough visible matter to hold it all in. It's as if a giant invisible hand is holding the galaxy together, wrapping around it in a silent, stabilizing embrace. This is where dark matter makes its grand entrance, at least in theory. It doesn't shine, it doesn't glow, but it sure knows how to tug. The math is relentless. In the 1970s, Vera Rubin and Kent Ford studied the Andromeda Galaxy, our neighbor, and mapped out the velocities of its stars. What they found stunned them. The rotation curve, a graph showing how fast stars move at different distances from the center, was flat. Like, unsettlingly flat. That wasn't supposed to happen. Rubin's work confirmed what Zwicky had hinted at decades earlier. There was missing mass, something unseen. She didn't call it dark matter herself, but her results lit a fire in the astrophysics world. And here's your historical fact of the day: Vera Rubin's groundbreaking discoveries were, for many years, quietly dismissed because she was a woman in a field that barely allowed women in. Historians still argue whether the full impact of her work was delayed because of this bias. Now you float alongside the edge of a rotating galaxy. You feel that faint pull, like a ghost tether tying stars together. And you start to sense the scale of this thing. If galaxies didn't have this extra, invisible mass, they'd disintegrate. Poof. Spun apart by their own motion. We wouldn't be here to talk about it. Or to whisper about it just before sleep. And here's a quirky little detour: some early scientists tried to explain these odd rotations by suggesting galaxies were filled with dim stars, dead suns, or rogue black holes. This group of possibilities got the catchy name MACHOs, Massive Astrophysical Compact Halo Objects. Imagine that acronym trying to survive in 2025. Unfortunately for MACHOs, observations never found enough of them to make up the difference. So MACHOs faded into the cosmic background, and dark matter took the lead. Back to your drifting self. You're hovering now over a galaxy cluster, hundreds of galaxies tied together in a gravitational ballet. You feel the complexity of it. Each galaxy, a swirl of stars. Each cluster, a chunk of the universe. Each movement, too stable, too fast, too strange. And you think, if this dark matter is real, it must be everywhere. Wrapped around galaxies in halos. Filling the voids between. Cradling the cosmos in an invisible net. Not touching light, not talking to it, just influencing it from the shadows. Now, here's the debate you didn't know you needed. Historians and physicists still argue whether dark matter is actually a thing, or whether gravity itself is broken at large scales. Maybe we need to rewrite the rules instead of adding new invisible stuff. Modified gravity theories, like MOND, we'll get to that later, make a compelling case. But they haven't dethroned dark matter just yet. For now, the simplest answer that fits all the awkward math is this: something invisible is out there. And it's massive. Not just, big guy at the gym, massive, but, shaping the universe, massive. So, you tuck yourself into this swirling galaxy, spinning peacefully in defiance of physics, and let the quiet tension between what's seen and unseen pull you deeper into the night. You're still floating, and now, space gets a bit rowdy. You find yourself watching two entire galaxy clusters collide, an event so grand and chaotic that you can actually feel it ripple through the darkness around you. This isn't a gentle merging. This is a cosmic car crash, in slow motion, over millions of years. This spectacle has a name, the Bullet Cluster. Imagine two galaxy clusters barreling through each other like speeding trains, each packed with hundreds of billions of stars, rivers of superheated gas, and, presumably, tons of dark matter. When they meet, it's not pretty. Galaxies slide past each other, barely interacting. Gas clouds smash together and glow like hot embers. But the weirdest part? The gravity doesn't line up with what you see. You float above the wreckage now, looking down. The glowing gas, the normal matter, has slammed together and heated up, right in the middle. That's the bright stuff. But gravitational lensing, how light bends around mass, tells a different story. It shows the strongest gravitational pull not in the middle, but off to the sides. Where the galaxies passed through. Where the invisible stuff, the presumed dark matter, would have gone. So here's the plot twist, the galaxies and their dark matter halos seem to have glided through like ghosts, barely slowed. But the normal matter, the gas, got caught in the mess. That means dark matter doesn't interact like regular matter does. It doesn't collide. It doesn't heat up. It just passes through, as if space itself is its only concern. This one collision, one giant, blurry image from telescopes, has become one of the strongest pieces of evidence that dark matter isn't just a math fix for galaxy spin curves. It's really there, pulling on light, acting like a separate substance. If you ever needed a smoking gun in astrophysics, this is it. But let's make it weird. Some fringe thinkers look at the bullet cluster and say, not so fast. They argue that the interpretation hinges on assumptions, that we know how all the matter in the cluster should behave, that there aren't other exotic forces at play. Maybe we're seeing something else entirely, some interaction or property we don't understand. You know how humans love to label things before fully understanding them. Historians still argue whether the bullet cluster settled the debate or just added fuel to a scientific fire already burning for decades. And that's what makes this so interesting, it's not just what we see, it's how we interpret the invisible clues. Let's take a quiet moment to admire how bizarre this is. You're looking at evidence for an invisible substance not because you see the thing itself, but because it didn't show up where it should have if it were ordinary matter. It showed up where gravity bent the light. That's like hearing a violin solo, turning your head, and realizing no one's holding the bow. Just, the melody, drifting through the air. And just for fun, here's your quirky tidbit, some scientists and sci-fi writers have playfully wondered if dark matter could be tied to a parallel universe bleeding into ours. Like shadows of another cosmos overlapping ours in gravitational ways. A fun idea. No evidence. But it sure makes your pillow feel softer. Back in your dreamlike drift, you float farther away from the bullet cluster, its chaos shrinking behind you like a memory. You can't see the dark matter, but its fingerprint lingers. A tug here. A bend in starlight there. The universe seems to whisper that something massive is out there, even if it refuses to introduce itself. So you keep moving. Slowly. Quietly. Past shattered galaxies and ghostly trails. You're hunting something that never leaves a trail, but leaves everything else dancing in response to its presence. Welcome to the greatest cosmic detective story never seen. As you float onward through the velvet dark, space begins to soften, not in texture, of course, but in meaning. You're drifting into a time when the universe itself was still being figured out. And the person at the center of it all? A familiar face. Albert Einstein. Now, Einstein didn't believe in dark matter. Not because he disagreed with the idea, but because, well, nobody had thought of it yet. You're rewinding time now. It's the early 1900s. Everything smells like ink and old paper. Einstein sits in front of a notebook, reshaping the laws of the cosmos with nothing but his brain. He's developing general relativity, his great theory of gravity. Not just a force anymore, but a curve in the very fabric of spacetime. You don't pull on an apple, space bends and the apple falls. But then, Einstein hits a problem. His equations say the universe should be expanding or contracting, but the astronomy of his time shows a static universe. No stretching, no collapsing. Just, chill. So what does he do? He adds a fudge factor, the cosmological constant. A repulsive force to balance gravity. A kind of anti-gravity baked into the universe. Something to make it sit still. That was Einstein's invisible addition. His version of plugging a mysterious force into the math just to make things work. Sound familiar? Later, when Edwin Hubble showed that the universe was expanding after all, Einstein reportedly called the cosmological constant his biggest blunder. Historians still argue whether he actually used those words. He might have just muttered something in German and stormed off, but the sentiment stuck. Sometimes, even geniuses patch holes with invisible forces. Fast forward to today, and here's a twist: the cosmological constant is back. In fact, it's one of the best explanations for dark energy, another invisible thing, separate from dark matter, that causes the universe's expansion to accelerate. Yes, accelerate. Like a car with no driver just pressing the gas harder. You float now between what Einstein saw and what he missed. The man who bent space with math, but couldn't bend it quite enough to imagine galaxies rotating too fast or clusters colliding invisibly. He gave us the language to describe the cosmos, but he also feared where the math might lead. Here's your quirky tidbit: Einstein once tried to get a job as a Swiss patent clerk because his professors didn't think he was professor material. Turns out, the universe had other plans. And now, the equations he sketched while reviewing toaster designs describe everything from black holes to dark matter halos. But let's get back to that idea of patching reality. See, when something in science doesn't make sense, you've got two options: change the model, or change reality. Einstein chose to tweak the math to match the assumed universe. Later scientists looked at the spinning galaxies and said, wait a second, maybe we need to add invisible mass instead. And that's the tightrope science walks: when do you add a ghost, and when do you admit the building is crooked? Right now, dark matter is our ghost. It's the placeholder in the story. The assumed missing piece that must be there, or else the universe as we know it can't hold together. But ghosts are tricky. They demand trust without evidence. And that's what makes people, yes, even cosmologists, squirm. Some researchers argue we're in danger of doing what Einstein did. Maybe dark matter is our cosmological constant. Maybe it's our blunder waiting to be exposed. But maybe not. Because the universe, like any good mystery novel, loves its red herrings. And loves even more to wait until you're just drifting off to sleep to drop its wildest clues. As you coast through the mathematical echoes of Einstein's genius, you feel it again, that constant contradiction. The comfort of equations, and the itch that maybe they're lying. Or maybe they're pointing to something so strange, we haven't learned to see it yet. And here you are, tucked into spacetime's soft folds, letting gravity lull you deeper. Listening for secrets in the silence. Maybe Einstein's ghost is still out here, quietly adjusting the constants as you pass. You're drifting now through a universe that feels oddly soft, almost spongy. You pass through space that isn't quite smooth, not like a calm lake, but more like a block of Swiss cheese. Pocked. Lumpy. Full of holes where you didn't expect them. Welcome to the Swiss cheese model of reality. And no, it's not a dinner joke from physicists with a snack problem, it's a real concept used to explain the structure of the universe. Imagine the cosmos as a kind of giant ball of cheese. The solid parts are galaxies, stars, and matter, normal stuff. The holes? Empty space. Or more precisely, the places where something should be pulling, but isn't, because the force you expect to see, gravity from visible matter, just isn't enough. This idea became a way to help visualize general relativity in action. In one version, the holes are patches where matter is missing but curvature remains. You float through one now. It's quiet. No stars. No planets. But you still feel a tug, as if the hole itself has weight. And that's the unsettling thing. These holes, the gaps in your cosmic cheese, still have gravitational pull. Like gravity from nothing. From dark matter. Or perhaps, something even weirder. You try not to laugh. Cheese? Really? But then you remember, physicists are people too. They like food. And metaphors. Sometimes both at once. You pass near a galaxy cluster now, one of those massive ones held together by more invisible matter than visible. The cheese becomes denser here. But in the spaces between, the holes are vast. These voids stretch across hundreds of millions of light-years. They aren't truly empty, but they're close. And yet, when light passes through them, its path still bends, just a little. As if even the nothing is something. Here's your historical fact. In the 1980s, researchers using radio telescopes discovered these cosmic voids, giant spaces between galaxy clusters, by mapping hydrogen distribution in the universe. These voids aren't random. They form a web, a filamentary network with galaxies clustered along stringy structures and emptiness in between. A sort of cosmic scaffolding. And here's your fringe whisper. Some fringe cosmologists argue that dark matter is just our way of explaining how gravity works through the holes. That maybe we don't need new stuff, just better equations that can handle the lumpiness of space itself. Historians still argue whether this idea is brilliant or bonkers. Or both. But from your peaceful float among the intergalactic gaps, you start to wonder, what if space isn't just the background canvas, but part of the art itself? Even in these enormous voids, there's structure. Faint whispers of radiation. A few wandering particles. But most hauntingly, there's still mass. Not the kind you can hold. But the kind you feel, tugging gently as you drift. The deeper you go into these holes, the less confident you become in what's real. Is dark matter a thing? Or just the name for a behavior? A label for gravity acting up where no one invited it. You reach a zone where time feels stretchy. Not because you're dreaming, though maybe you are, but because light itself has been bent and delayed by invisible hands. Light traveling from faraway galaxies gets ever so slightly curved. Not just by what we can see, but by what we can't. These subtle deflections, observed in maps from space telescopes, tell us that something massive lurks in the shadows. You close your eyes, though they're already closed. You imagine slicing into this Swiss cheese of a universe, and seeing layers. Holes inside holes. Mass smeared like butter across bread. Everything, uneven. Which is somehow comforting. The universe, like your life, is not smooth. But it still holds together. And here's one final silly note before sleep overtakes you. Some early thinkers once proposed that all the hidden mass might come from interstellar snowballs, cold, frozen planets just floating in the dark. Imagine that. A universe filled with rogue ice cream scoops, keeping galaxies from flying apart. Not quite Nobel Prize worthy, but deliciously optimistic. So you drift, surrounded by unseen weight, curving space around you. The cheese may have holes, but it's still real. And something inside those holes is gently holding everything in place. You float deeper now, not through galaxies or clusters, but into something far more personal, yourself. Not your memories or thoughts or favorite socks, but your atoms. Take a moment. Imagine shrinking down. Past your skin, your bloodstream, your cells. Into the molecules. Into the atoms. You arrive at a single proton, and realize, you're in the middle of, mostly nothing. You see, your body, this warm, wonderful thing you drag through space and coffee shops, is 99.9999999% empty space. If the nucleus of an atom were the size of a pea, the nearest electron would be orbiting over 300 meters away. That's a football field of nothing. And everything between. Just raw, echoing distance. So you, listener, bedtime dreamer, you are, quite literally, made of void. A vibrating illusion of solidity created by electromagnetic forces. And yet, when you fall out of bed, you thud. Isn't that delightful? Dark matter, as it turns out, might be the same kind of joke, something that feels dense and important, yet refuses to show its face. Maybe it's just made of particles that don't like to interact with ours. Shy particles. Ghost particles. These potential culprits have names, of course. The frontrunner? WIMPs, weakly interacting massive particles. They sound like comic book sidekicks, but they're serious business. Heavy enough to matter, yet so antisocial they rarely bump into anything we can detect. You're now hovering above a deep underground laboratory, buried beneath a mountain in Italy. Inside, scientists are trying to catch a WIMP in the act, just one interaction. One little bump. It would be like hearing a single snowflake land in a city during a blizzard. The detectors are bathed in liquid xenon and shielded from cosmic rays. They wait. They watch. Mostly, they get silence. Here's your mainstream historical fact: these underground experiments started seriously picking up in the 1990s and 2000s, with detectors like Dama/Libra, LUX, and now Axion leading the charge. The idea is to detect rare nuclear recoils caused by a WIMP smacking into a normal atom. But so far, crickets. And here's a delightfully fringe theory for balance: maybe dark matter isn't made of particles at all. Maybe it's made of waves, quantum fields humming through space. One popular contender here is the axion. It's even more ghostly than a WIMP. And yes, it's named after a brand of laundry detergent. The physicist who came up with the name liked the sound of it. Dark matter, now lemon-scented. Historians still argue whether WIMPs are a brilliant solution or a money pit, swallowing decades of effort with no results. Some physicists are frustrated. Some keep digging. The dark matter race is a bit like dating someone for 20 years who refuses to appear in photographs. You float now through one of those detectors, shrunk to subatomic size. The silence is deafening. You wait. You hope. Maybe tonight's the night something brushes against your atoms. Maybe a particle from the early universe will choose you. But, probably not. This is where your thoughts begin to fray. If most of what you're made of is empty space, and most of the universe is made of invisible stuff, what is anything, really? What counts as real? Mass? Touch? Visibility? Or just, effect? Because here's the thing, dark matter might never be caught. It might never flash across a detector or leave a mark on a graph. But it still bends galaxies. It still holds things together. It still has consequences. Just like gravity. Just like you. You begin to feel less like a person and more like a soft ripple in the field of existence. A blip in probability. A pause in the void. So you settle into your place between the particles. Your lungs full of emptiness. Your skin a thin suggestion of matter. You, the person made of mostly nothing, are drifting through a universe also made of mostly nothing, and still, somehow, everything is something. Even if we can't see it. You've slipped even deeper now, beneath the silence of atoms and the whisper of stars. Down here, in the underground layers of science, machines hum quietly, surrounded by layers of concrete, earth, and lead shielding. You're in the company of physicists who spend their entire careers listening for particles that may never speak. This is the strange world of dark matter detectors, chasing invisible things with unbearable patience. You hover next to one now, Xenon, hidden beneath the Gran Sasso Mountains in Italy. Its heart is filled with ultrapure liquid xenon, cold enough to sting space itself. The idea is simple but brilliant: if a WIMP, a weakly interacting massive particle, happens to crash into one of these xenon atoms, it'll make a tiny flash. A photon. A flicker. Maybe even a ripple of electrons. Then, bam, we've got something. Only, it hasn't happened. Not in a clear, definitive way. That's where the desperation starts to creep in. You peek over the shoulders of scientists staring at endless screens of nothing. But this nothing means everything. A clean graph. A quiet dataset. A lack of noise is still a message, it's just a frustrating one. WIMPs were the superstar candidates for decades. They'd fit perfectly into the standard model of particle physics, well, almost. They'd solve not only dark matter but maybe even explain why particles have the masses they do. It would have been neat. Predictable. Elegant. But neatness is not the universe's strong suit. So the physicists branched out. From WIMPs to axions, sterile neutrinos, and other even more elusive things. Axions, in particular, are weird. They might be everywhere, forming a field instead of individual particles, like a fog you can't breathe. You wouldn't even feel them. But they might bend light slightly. Or tickle a magnetic field. Here's a quirky tidbit for your dreams. One experiment trying to find axions is literally called the Axion Dark Matter Experiment, or ADMX. It's like naming your dating app, Find My Wife. Bold. Then there's LUX Zeppelin in South Dakota, deep inside a former gold mine. Or Panda X in China. Or Super CDMS in Canada. They all do roughly the same thing: wait and hope. But so far, every time they think they hear a whisper, a possible blip, it turns out to be something mundane. Radioactive decay. A cosmic ray that snuck in. A squirrel chewing on the data cables. Okay, not that last one, yet. And here's the kicker: historians and physicists still argue whether we're chasing a ghost or refining a delusion. Some ask, what if dark matter doesn't interact with anything at all? Not even weakly? What if it's completely beyond our ability to touch? You pause now and realize how human this all is. Searching for something we can't see, hoping to find it by how it moves the things we can. It's like tracking a bird by the wind it leaves behind. Now, you float through another experiment, but this one is in space. Aboard the Alpha Magnetic Spectrometer, AMS-02, strapped to the side of the International Space Station, silently collecting cosmic rays. It watches for exotic particles that might come from dark matter collisions. A dark particle smashing into another dark particle and producing something we can see. And yet, the data remains inconclusive. There's a sort of romantic tragedy to it all: thousands of scientists, billions of dollars, countless hours, chasing silence. Imagine a world where all this effort pays off with a single, undeniable flash. That tiny moment of proof would rewrite our understanding of the universe. Confirm that the invisible scaffold we believed in for so long is real. But for now, the silence continues. And in that silence, there is a kind of peace. Like sitting beside a sleeping cat, knowing that something alive is there, even if it doesn't stir. So you drift quietly from lab to lab, mountain to mountain, detector to detector. Listening. Waiting. Holding your breath for a flash in the dark. And as you fade into the quiet, you realize something simple and true: even if these particles never show themselves, the journey to find them has already changed us. Given us better tools, better questions, better patience. We may never catch a WIMP. But the chase has made us more human. You drift now into deeper thought, a cozy and unsettling place at once, a quiet pocket of doubt. The stars continue to whirl around their galactic centers, held firm by unseen hands. The math keeps pointing to something missing. The experiments keep blinking in silence. So here comes the uncomfortable question that sits like a pebble under your cosmic pillow. What if dark matter doesn't exist at all? Breathe that in for a second. What if this whole idea, 85% of a universe made of some undetectable, invisible stuff, is just our best guess? A placeholder? A necessary fudge factor we inserted because the math didn't line up? It wouldn't be the first time. Science has a long history of explaining things by inventing invisible forces. Once upon a time, we believed in the ether, a mystical substance thought to carry light waves through the void, like air carries sound. For centuries, the ether was considered real. Until, it wasn't. Dark matter might be a modern version of that. Some physicists have dared to ask, what if we're solving the wrong problem? Because here's what we know. Gravity is the boss of large-scale motion. It shapes planets, galaxies, the entire cosmic web. And dark matter was introduced not because we saw it, but because gravity was acting weird. So, what if it's not about the matter being missing? What if gravity itself is misunderstood? You slowly orbit around that idea now. A soft swirl of possibility. Could it be that Newton and Einstein gave us equations that work perfectly for apples and satellites, but not for galaxies and the expanding universe? This line of thinking gave rise to alternatives. The most famous of them is modified Newtonian dynamics. We'll explore it more later, but in short, Mond suggests that gravity might behave differently when it's really, really weak, like out at the edges of galaxies. Maybe, just maybe, we don't need extra matter. Maybe we just need to update the rules. It's like discovering your GPS always says you're off by 20 meters, not because you're lost, but because the map was drawn funny. Some scientists argue that clinging to dark matter is an emotional choice. We've invested so much time and effort chasing it that to give up now would feel like betrayal. Others say no, that dark matter is the only thing that consistently explains everything from galaxy spins to the cosmic microwave background. Historians still argue whether this debate echoes the 19th century struggle over whether light was a particle or a wave. Spoiler, it turned out to be both. Maybe dark matter is a similar riddle. A false divide. Something stranger than either side expects. Let's not forget the philosophical part. Humans love naming things. If we don't understand something, we give it a label. Dark matter is less a discovery and more a description of ignorance. A poetic name for a gap in our understanding. And here's a little quirky detour for your sleepy mind, there's a real proposal out there that gravity leaks into other dimensions. Like, actual extra dimensions. In that case, the strange motions of stars wouldn't be caused by invisible matter, but by gravity bleeding into realms we can't perceive. It's a sci-fi idea wrapped in real math. You float now through this field of doubt, feeling it thicken around you like cosmic fog. There's comfort in it, weirdly. Because even if dark matter isn't real, the clues it leaves behind are. The universe is still behaving strangely. And that's the most exciting part. Maybe one day we'll look back and laugh. Remember when we thought there were invisible halos around galaxies? And maybe, by then, we'll have something better. A new theory. A new particle. A new perspective. But tonight? Tonight, you rest in that tension. The not knowing. The soft contradiction. Is dark matter real? Or is reality just darker than we thought? You drift now into a quieter part of the universe, not physically quieter, but conceptually so. A zone not full of galaxies or exotic particles, but background noise. Cosmic background noise, to be precise. You've arrived at the cosmic microwave background, or CMB. Picture the universe just 380,000 years old, basically a cranky infant. It's no longer a chaotic plasma soup, but it's still glowing from the heat of its own birth. That glow is now stretched thin across space and time, like the fading echo of a scream. And here's the twist, this ancient glow may hold some of the strongest clues about dark matter. You float beside a satellite now, Planck, or maybe WMAP before it, mapping the sky not in light, but in temperature. And not just hot and cold, but barely warmer, slightly cooler. Differences of millionths of a degree. These tiny fluctuations. They're fingerprints of structure. They show how matter began to clump. How some areas attracted more mass. How galaxies would one day form. But here's the key, the pattern only makes sense if there's dark matter in the mix. Without dark matter, the clumps form too slowly. The math just doesn't work. The baby universe needed something extra, something massive that could start tugging normal matter into place before the light even cooled. That's why physicists love the CMB. It's not just a pretty sky map. It's evidence. Quiet, ancient, beautiful evidence. But, of course, here comes the debate. Because historians and cosmologists still argue whether the CMB can be explained without invoking dark matter. Maybe modified gravity can also fit the pattern, with a few tweaks. Maybe our models are too clean, too idealized. Real space might be messier than the simulations. And here's your quirky bedtime fact, the CMB isn't just a science thing. In 1965, two radio engineers, Penzias and Wilson, accidentally discovered it while trying to remove background static from a radio antenna. They thought it was bird poop. Literally. They cleaned the dish. The noise stayed. Turns out, it was the afterglow of the Big Bang. That's how humble cosmic discovery can be. A Nobel Prize, born from stubborn static. Now back to your gentle drift. You float between ancient waves of light, curling faintly around you like warm breath in cold air. These photons have traveled for nearly 14 billion years, uninterrupted, until they reached detectors and told their story. The CMB shows us the early blueprint of the universe. The dots and squiggles in its temperature map correspond to the distribution of matter across space. But there's more there than meets the eye. The clumping, the structure, the harmony, it sings of something unseen shaping the pattern from behind the curtain. Imagine frosting a cake by throwing invisible hands at it. That's what dark matter did to the early universe. It pulled the batter into place before the cosmic oven even finished preheating. But again, no direct detection. Just indirect effects. Just whispers. And that's the tension. The CMB is one of the strongest arguments for dark matter, yet it still doesn't prove what it is. So you drift farther into the afterglow, among the pixelated pattern of the early cosmos. It's like reading a baby photo of reality itself. You realize something profound, even in its infancy, the universe was already carrying secrets it hasn't yet told us. And just before you let go, you wonder. What else is hidden in the hum? You're weightless now in a space that feels different, not cold, not warm, just curious. A soft hum builds around you, not from machines or galaxies, but from a different kind of structure entirely. You've floated into the cosmic web, the largest pattern in the universe. Imagine a spider's web stretched across billions of light-years, but glowing faintly with galaxies instead of dewdrops. Long filaments of matter twist and connect, forming tendrils that bind clusters together. These threads aren't solid. They're scaffolds. And what fills them, what outlines them, isn't just ordinary matter. It's dark matter. Or at least, that's the working theory. You hover at the intersection of two great filaments. This crossing point, called a node, is where galaxy clusters form, dense hubs of activity. The strands leading into them are quieter, but no less important. They're the connective tissue of the universe. And these shapes? They weren't random. They grew this way, stretched and pulled into shape by gravity. But not gravity from things you can see. There wasn't enough ordinary matter to do the job. So once again, something else had to be there. Something invisible. Something silent. Something dark. Cosmological simulations confirm it. Plug in the math, include dark matter, and these vast structures emerge. The shapes match the real thing. Without dark matter, the web unravels. The universe looks wrong. Too flat. Too loose. Too empty. Here's your mainstream historical note. In the late 20th century, computer simulations like the Millennium Simulation began to model the universe using billions of particles. Scientists could grow a universe in the computer, from the Big Bang to the present day. With dark matter included, the cosmic web forms beautifully. Without it, it's like baking a cake without flour. Just collapse and goo. Now, here's your quirky, just before bedtime twist. Some astrophysicists describe the web as a cosmic brain. The scale, the shape, it eerily resembles neural networks. Galaxies like neurons. Filaments like axions. It's not proof of anything spooky. Just a fun comparison. But it makes you think. What if the universe is thinking? Back in your drift, you glide along one of the great filaments. It's massive. But also mostly empty. You pass through it like a leaf caught in a breeze. You can't see the dark matter, but you can feel it in how the galaxies cling to the web, not scattered randomly but drawn like beads along a thread. This structure, this invisible design, it's not just elegant. It's essential. And yet, again, we've never seen the thing shaping it. Never photographed a dark matter particle. Never touched it. Only measured the architecture it leaves behind. Historians and theorists still argue whether this structure is enough to confirm dark matter, or whether, once again, we're chasing an effect without catching the cause. Some alternative theories say the web might form just from modified gravity laws. Others suggest interactions between ordinary matter and early energy fields could mimic the pattern. But the simplest model, the one that keeps surviving peer review, still relies on dark matter. And you can't help but respect it. This, ghost architecture. It doesn't speak. It doesn't shine. But it's shaped everything. It's the bones beneath the stars. The outline of the invisible. You pause at a lonely stretch of the filament, deep in the intergalactic void. You look around. The galaxies are far away now. Their light barely reaches you. And yet, you don't feel alone. The thread still holds you. The quiet mass is still there, cradling the space between things. You exhale. You didn't know you were holding your breath. Even the empty places in the universe have form. Even nothing can be part of the structure. So you float, gently, on this invisible thread. And for now, you're home. You stir softly in your drift, now guided not by stars or clusters, but by motion, ancient, swirling, relentless motion. You've reached the part of the universe that spins in ways it shouldn't. You're hovering just outside the edge of a galaxy now. One not unlike the Milky Way. You can see the stars, like grains of sugar on a spiraling plate. The arms rotate gracefully, and you notice something odd, they're moving too fast. That's right. The stars on the outer edge of this galaxy are zipping around at incredible speeds. And here's the catch, according to Newton and Einstein, they shouldn't be. You know the drill. Gravity depends on mass. The more mass in the center of the galaxy, the more tightly the stars at the edge should be bound. But the math says those distant stars should be moving much slower, or they should have been flung off into space eons ago. But they haven't. They're still there. Still circling. Still defying the rules. And so, back in the 1970s, an astronomer named Vera Rubin decided to measure these galactic speeds precisely. What she found was astonishing, and consistent. In galaxy after galaxy, the rotation curves, a fancy word for star speeds as a function of distance from the center, stayed flat. They didn't drop off. They held steady. This observation was one of the first solid, empirical hints that something invisible was holding galaxies together. Rubin didn't shout about dark matter right away. She was careful, skeptical, precise. But the results were clear. If there wasn't more mass than what we could see, then galaxies simply shouldn't look like they do. They shouldn't hold together. But they do. So, cue the ghost. Dark matter entered the scene, not as a wild guess, but as a necessary correction. A patch for reality. Here's your quirky tidbit: Vera Rubin, for all her groundbreaking discoveries, was snubbed by the Nobel Prize Committee throughout her lifetime. Despite fundamentally shifting our understanding of the universe, she was never honored with the prize. A gentle reminder that sometimes, invisibility isn't just cosmic. As you hover above the spinning galaxy, you can almost see the invisible halo. Not with your eyes, but with your intuition. It surrounds the entire structure, far beyond the visible disk. A massive, spherical cloud of unseen mass, gently tethering every star. This halo model of dark matter has become standard. Every galaxy, we believe, swims in its own personal bubble of dark matter. Like a swimmer moving through invisible water, the galaxy spins thanks to the pull of this hidden mass. And historians and theorists still argue whether this is the only explanation. Could the stars be moving fast because gravity behaves differently at low accelerations? That's what modified Newtonian dynamics, MOND, suggests. MOND isn't about adding matter, it's about tweaking the laws. Imagine gravity having a split personality, one way for apples and planets, another way for galaxies. It sounds wild, but in many tests, MOND actually fits the data. In some galaxies, MOND predicts rotation curves better than dark matter models. But, not in all. And that's the issue. MOND can't quite explain clusters, or the bullet cluster, or the cosmic microwave background. It works in a few places, but fails in others. Dark matter, on the other hand, feels more consistent, more universal, even if it's also invisible. And so, your thoughts swirl like the stars below. You watch the spinning continue, hypnotic and impossible. You let the motion carry you forward, as if tethered by an invisible string. And maybe, that's exactly what you are. The galaxy doesn't care if you understand why it spins. It just does. And you? You keep drifting, spiraling into mystery. You're spinning now, not in circles like the stars, but in questions. Each one orbiting closer and closer to something stranger. Because dark matter doesn't just shape galaxies. It also collides. Yes. Collides. You drift toward a deep scar in the fabric of space, a place known as the bullet cluster. Two galaxy clusters smashed into each other here, over 100 million years ago, and left behind something no one quite expected. Imagine two clouds of stars passing through one another, galaxies, mostly empty space, slipping by with barely a scratch. But between them is gas. Hot, dense, X-ray blasting gas. And when the clusters collided, that gas, unlike the galaxies, slammed together. It slowed down. Heated up. Left a visible shockwave in the X-ray spectrum. But here's the twist: when astronomers mapped the gravity in the aftermath of this crash, they found that most of the mass, the stuff tugging on light, was not with the slowed-down gas. It was with the galaxies. The ones that passed straight through. It was as if the mass itself had ignored the collision. And that, dear dreamer, is where dark matter entered the room wearing sunglasses and sipping a silent cocktail. The only explanation that made sense. Most of the mass in those clusters had passed through without interacting, exactly what dark matter is supposed to do. The bullet cluster became a visual, empirical gut punch of evidence. It was like a crime scene where the visible matter was caught in a struggle, but the gravitational fingerprints pointed somewhere else entirely. This wasn't just a mystery anymore, it was a clue. A glowing neon clue with an arrow. And here's your historical fact: the bullet cluster's light was observed using the Chandra X-ray Observatory and mapped with gravitational lensing techniques, which showed how the cluster's mass warped the light from more distant galaxies behind it. The result? A kind of cosmic X-ray plus MRI, two scans of the same patient, telling very different stories. But of course, not everyone agrees on the diagnosis. Historians and cosmologists still argue whether the bullet cluster proves dark matter exists, or just supports it very strongly. Could modified gravity theories explain this? Could another force be at play? Mond, for example, struggles here. Its predictions don't line up well with what we see. But Mond isn't the only alternative in town. Some fringe theories suggest we're seeing something even more radical, interacting dark matter, or even mirror matter, a whole parallel sector of physics, invisible and untouchable. Others suggest quantum gravity effects that don't behave in any way we currently understand. The bullet cluster doesn't settle the matter. But it pushes dark matter theories far into the lead. Here's your quirky fact for the night: there's a second cluster just like it, El Gordo. Yes, the fat one. Astronomers love their drama. El Gordo is bigger, hotter, and louder than the bullet cluster. A cosmic heavyweight brawl with similar gravitational mismatches. And it, too, whispers the same thing: something invisible passed through here. Now, you float through the aftermath. Past galaxies drifting quietly in post-collision calm. Past the hot gas glowing in X-ray, like embers of a great fire. Past the lensing distortions, starlight bent by gravity like ripples in glass. And everywhere you look, you feel that tension again. We can't see it. We can't touch it. But we can trace it. It behaves like matter. It gravitates like matter. It shows up in the most violent, undeniable places in the cosmos. It doesn't flinch. And yet, we still don't know what it is. It's like hearing footsteps in the hall every night and still not catching who's walking. You start to wonder if they're real. Or if they're part of the house itself. But for now, you accept the truth: something passed through. Something invisible, weighty, and undeniable. You curl into the thought. Let it wrap around you like spacetime around a mass. You don't need all the answers tonight. Just a little more wonder. You're adrift now, not through space, but through theory, suspended in equations, stitched together by thought. You've seen stars spin, galaxies curve, clusters collide, all whispering the name of something we cannot see. And yet, despite all that evidence, you feel it: the models don't quite settle. They wobble. There's always an exception. A place where the math twitches. Welcome to the world of modified gravity. You glide gently through the minds of scientists who dared to say, maybe the problem isn't that matter is missing. Maybe the problem is us. Our understanding. Our assumptions. It starts with something called MOND, modified Newtonian dynamics. Invented by physicist Mordechai Milgram in the early 1980s, it's simple at heart: Newton's laws might break down at very low accelerations, like those found on the outer edges of galaxies. In MOND, gravity gets a little stronger when things are barely moving. Just enough to explain flat galaxy rotation curves, without needing dark matter at all. And it works. Kind of shockingly well. In fact, MOND can predict the motions of certain galaxies better than dark matter models, especially smaller ones, like dwarf galaxies, where the visible mass is easier to measure. You pause here, surprised. Could that be it? Have we just been using the wrong rulebook all along? But there's a catch. Or several. MOND struggles when it leaves galaxies and tries to explain galaxy clusters, gravitational lensing, or the cosmic microwave background. It's a rule that works locally, but not globally. Like a great local band that can't sell tickets on tour. So MOND evolved. Enter TeVis, emergent gravity, entropic gravity, and others. These are modified gravity theories that try to go big, to do everything dark matter does, and more, without invoking invisible particles. Some rely on new fields. Some play with quantum information. One even suggests gravity is a byproduct of the universe trying to organize itself, like a cosmic version of spring cleaning. And yet, they all hit walls. Places where the observations laugh and say, try again. Here's your historical fact: MOND was once dismissed as fringe, but its predictive power, particularly with low surface brightness galaxies, forced mainstream astrophysicists to pay attention. Not to embrace it entirely, but to respect the questions it raised. And your quirky thought for the night: there's a flavor of modified gravity called F.R., gravity that tweaks Einstein's equations by changing a single letter. Literally. From R to F.R. It's the mathematical equivalent of saying, what if we just remix the main theme of the universe? Still, historians and physicists continue to argue: is it more likely that there's invisible matter we can't detect? Or that the laws of the universe need revising? It's a philosophical divide, as much as a scientific one. Do we trust the rules and doubt our senses? Or trust what we see and assume the rules are flawed? You're floating now between two chalkboards, each covered in beautiful hieroglyphics of math. One sings the song of particles. The other hums with elegant curves of modified gravity. You can't decide which melody feels more real. So you let both play. Because in truth, the universe might be more complicated than either side allows. Maybe it's not dark matter or modified gravity. Maybe it's something else. Or both. Or neither. And in that mystery, you feel no fear. Just warmth. Not knowing is where all curiosity begins. So you stretch your limbs in the weightlessness of unproven ideas. You imagine rewriting Newton in the margins. You picture Einstein raising one eyebrow from the back of the room. And you float on, guided not by certainty, but by the beautiful gravity of questions. You've journeyed through spinning galaxies, colliding clusters, invisible scaffolds, and silent detectors. You've hovered in equations and echoed in microwave radiation. And now, you're drifting toward the edges, the places where dark matter gets weirder, wilder, and possibly, wrong. This is the realm of dark matter alternatives. Not theories that tweak gravity. Not models that say, oh, we just can't see it yet. No, these are ideas that suggest, what if dark matter is something completely different? First up. Self-interacting dark matter. In the standard model, dark matter is aloof. It doesn't talk to light. Doesn't bump into regular matter. Doesn't even talk to itself. But what if it does? What if dark matter can nudge other dark matter? Imagine a ghost that can punch another ghost. This idea helps explain a few mysteries, like why some galaxy cores seem less dense than dark matter predicts. Or why small galaxies get shredded near bigger ones. Self-interactions could smooth things out, prevent overcrowding, keep the universe a little tidier. But there's a balancing act. Too much interaction, and dark matter becomes visible. Too little, and it's the same old WIMP story. So theorists dance on that thin wire, adjusting parameters like chefs seasoning a stew. Now you float sideways into something stranger, fuzzy dark matter. This model replaces particles with waves. Quantum waves, spread out over light years. Instead of tiny bullet-like WIMPs, fuzzy dark matter acts more like a fog. It doesn't clump the same way. It flows. It pulses. It could solve some problems that plague small galaxies, like why they don't always behave like simulations say they should. Picture this: entire galaxies, swaddled in a soft halo of vibration, like a whisper you can't quite hear. That's fuzzy dark matter. Cozy, isn't it? Here's your quirky fact: these ideas require ultralight particles, so light that a single one could stretch across a galaxy. We're talking 10 to the power of -22 electron volts. That's roughly a million trillion times lighter than a proton. If these particles existed in your room, they'd pass through you like mist. They wouldn't knock your coffee off the table. They wouldn't even notice your atoms. Another idea? Mirror matter. It proposes an entire parallel world, particles that mirror our own, but never interact with them except through gravity. A shadow universe. Think of it as a reflection behind the glass of reality. The particles in that universe could have mirror stars, mirror galaxies, even mirror life. Don't worry, the mirror you doesn't snore. But back to physics. Why invent such strange things? Because we're desperate for answers. And desperate minds create delightful possibilities. Historians and cosmologists still argue whether these models are strokes of genius, or cosmic fan fiction. Many of them are nearly impossible to test. Others make predictions that haven't matched the data, yet. But that's the thrill of the frontier. You're now drifting through the outer edge of theory, past comfort, beyond the textbooks. Here, imagination wears a lab coat. And hovering ahead is a recent contender, dark fluid. What if dark matter isn't matter at all? What if it's not particles, not waves, but something in between? A field. A fluid. A pressure, seeping through the cosmos. One that mimics dark matter and dark energy. Two birds. One weird stone. These are not mainstream yet. But they're gaining attention. Slowly. Like shadows growing longer at dusk. You pause. A silence forms around you, not of absence, but of potential. Because if even one of these models is right, the universe becomes something wildly different than we thought. Something softer. Stranger. More layered. Less binary. And as you turn slowly in the nothingness, you realize this: the longer we search for dark matter, the more it teaches us, about persistence, about creativity, and about the humility of not knowing. The darkness has become its own kind of light. You've arrived now at the final bend of the road, a quiet place, where discovery meets reflection. Not every mystery gets solved. Some become companions. Like the stars above your head, dark matter has gone from question to presence. And yet, you still don't know what it is. You're not alone in this. Over the past century, generations of astronomers, physicists, engineers, and thinkers have poured lifetimes into this riddle. Each decade, new clues. Each decade, new doubts. Still no particle. Still no signal. But still, something unseen pulls galaxies, bends light, and gives structure to everything. You hover now at the edge of the observable universe, looking out across a sea of 13.8 billion years. You see not darkness, but structure. A lattice of galaxies, stretched across time like golden threads. This is where dark matter's fingerprints are most obvious. The early universe, tiny ripples in the cosmic microwave background, gave way to galaxies, stars, and you. But none of that could have happened without a silent, gravitational tug. Something gave structure to the nothing. Something seeded the web. That something still doesn't shine. But it holds everything together. Here's your historical anchor: dark matter isn't a fringe idea anymore. It's the bedrock of the lambda-CDM model, our best understanding of how the universe works. Without it, the model crumbles. Predictions fall apart. Simulations go sideways. It's like baking a cake without flour and pretending it's just, really airy mousse. Still, historians and philosophers argue whether this means dark matter is real, or just a very useful illusion. After all, the Ptolemaic model of epicycles predicted planetary motion just fine, until we realized it was all wrong. And maybe that's where the beauty lies. Not in certainty, but in the questions themselves. You drift back through your journey now, past Vera Rubin's galaxies, the bullet cluster's ghost collisions, the soft fog of fuzzy matter, the tickling possibilities of modified gravity. Each moment stitched into the quilt of a universe we almost understand. Here's your quirky final fact: scientists have proposed building dark matter detectors on the moon. Why? Less noise. No atmosphere. Fewer squirrels chewing wires. It sounds like science fiction. But if there's one thing dark matter has taught us, it's that the line between imagination and discovery is paper thin. Now, you curl into this last thought like a blanket. What if we never find dark matter? What if it stays invisible forever? Would that mean we failed? Or would it mean we were brave enough to reach for something we could never quite grasp, but tried anyway? You know the answer. It's the trying that matters. The questions that pull us forward. The invisible tug that keeps science alive. So you close your eyes, not in frustration, but in peace. You've followed the clues. Walked the spiral arms. Drifted through the fabric of gravity and light. And though dark matter remains in the shadows, its story is now part of yours. Now, breathe out. Let the questions float away for a moment. You don't need to hold them all. Not tonight. Picture the galaxies you visited, spinning like quiet pinwheels in the distance, still wrapped in invisible halos. You don't need to understand them. You just need to know they're there. Let your mind soften. Loosen. Unclench from the gravity of ideas. The stars are still moving. The universe is still expanding. The mystery is still alive. And that's more than enough. Maybe someday we'll name the particle. Maybe it's already in the data, waiting to be noticed. Or maybe we're wrong about all of it. Maybe the truth is bigger, or simpler, or stranger than anything we've imagined so far. But tonight, under the soft blanket of cosmic silence, none of that matters. You are a tiny voice in a vast dark sea, yes, but also a light that asks questions. That listens for answers. That wonders. And wonder is the first step toward understanding. So let yourself sink now into that stillness. The stars can keep spinning without you for a while. The equations can wait. You've done enough for tonight. Sweet dreams, traveler.